to provide a brief introduction to covariance and correlation. So first I'll tell you what they are, and then I'll show you in Excel how you can easily compute them. And covariance and correlation are commonly used in all kinds of analyses in the sciences as well as in finance and economics. So the covariance really measures the relationship between two variables, in this case x and y. And what you're doing is you're essentially averaging the deviation from x multiplied by the deviation from y. And you're dividing it by, in this case, 1 divided by n minus 1. So this is a sample covariance. If you were dividing by 1 over n, you'd be getting a population covariance. So let's just think about how this works intuitively. So if most of the time when x is above its average, y is also above its average, you get a positive number here times a positive number here, you get a positive number. Okay, it doesn't have to be that way in every single situation, but let's say most of the time that occurs. If most of the time when x is doing poorly, it's below its average, y is also doing poorly and is below its average, you get a negative times a negative, which also gives you a positive number. That's the case where you're going to get a positive covariance, which means they have a positive relationship. They tend to move up and down together. Okay, when x is doing better than average, y is doing better than average. When x is doing worse than average, y is doing worse than average. Now consider the case where when x does better than average, this would be positive, y is doing worse than average, negative. Positive times a negative gives you a negative number. Again, it doesn't happen to have to happen every single time, but let's say most of the time that happens. If most of the time when x is doing worse than average, negative number, y is doing better than average, positive number, negative times a positive gives us a negative number, that's where we get this negative covariance, which has a negative relationship. They tend to move in opposite directions. You can also have the case where the covariance is zero, that there's no linear relationship. There may be some kind of relationship, but it's not linear. So, sometimes x is doing better than average, y is doing better than average. Sometimes x is doing better than average, y is doing worse than average. Okay, can't really figure anything out. The problem with covariance is that, for example, if you were looking at two sets of variables, a and b, and c and d, and a and b had a covariance of 10, and c and d had a covariance of 100, you couldn't say that c and d were 10 times more strongly related or more positively related than a and b. And that has to do with the units of x and y, or of a and b and c and d. So what we oftentimes do is we scale it to something known as correlation. Correlation here is denoted by the Greek letter rho. So correlation is the covariance divided by the standard deviation of x times the standard deviation of y. And it's going to be between -1 and +1. -1 means perfect negative correlation. It means that when x goes up, y always goes down, and always by the same proportion. So maybe if x goes up by 1 unit, y goes down by 2 units, and that relationship always holds. So if you tell me what x did, I'll tell you exactly where y is. +1 means perfect positive correlation. It means that when x goes up, y always goes up, and again, by the same proportions all the time. So maybe when x goes up, y goes up by 3 units. So x goes up by 1 unit, y goes up by 3 units. And that relationship always holds. So that if you know what x did, you know what y did. Or if you know what y did, you know what x did. Most of the time, you're going to be somewhere in between those. You're not going to have perfect positive or perfect negative. You're going to be somewhere in between. Let's take a look at a couple of graphs here. So a positive covariance or a positive correlation is a case where, they tend to move in the same direction. Here, x is doing worse than average, right? It's negative. Y is also doing worse than average in these two cases. Here, X is doing better than average, Y is doing better than average, both positive, etc., etc. Perfect positive correlation would be all of these points were exactly on this line. So if you told me what X was, I would know exactly what Y was. A negative covariance goes in the opposite direction. Here, X is doing poorly, Y is doing well. Here, X is doing okay, Y is doing poorly. So they're moving in opposite directions as indicated by this line here, which seems to do a pretty good job of describing the relationship between X and Y. So you can see here, and again, if we wanted perfect negative correlation, or if we had perfect negative correlation, all of these points would lie on this line. So you would know exactly where, if you knew what X did, you'd know exactly where Y was. Okay, and the last relationship is this zero covariance. So this is the case where, X is doing poorly, X is negative, Y is negative. X is negative, Y is positive, right? This doesn't seem to be an exact relationship, right? Sometimes, they're both, up. Sometimes they're both down. Sometimes one is up and one is down. Okay, can't find any relationship. It would be hard to draw a line here that represented this relationship. So let's take a look at how we compute this in Excel. So I have some data here. Okay, I have A and B, and I have C and D. So I have two sets of data here. So let me calculate the covariance first of A and B. So it's a fairly tedious equation, but you can certainly do it by hand. But one way to do it is to take advantage of the functions in Excel. So you can see down here we have covariance.p, that's for the population covariance, and covariance.s, that's for the sample covariance. So the difference is the population divides by n, the sample divides by n minus 1, which makes it a little bit bigger. Okay, let's do the sample covariance. All right, and what you're going to do is you're going to type in that, and then it's going to ask you for the first array, or the first set of numbers. And I'm going to put a comma in. And then the second set is going to be B. And I'll close up the parentheses, and let's see what we get here. We get a covariance of 2.5333. All right, let's do it for C and D. We'll do the same thing, equals and we have these variables. And these variables. Here we get one of 98. It's much bigger. In fact, let me see if I can make my screen a little bit bigger here for you to see. So you can see this is much larger. But is this more strongly related, these two, than this? You can't really tell. These are much smaller units. In fact, these units tend to be, actually for B, they tend to be 10 times larger. These are almost 10 times larger. I fooled around with the numbers to try and make my point, but these have bigger units, so they're going to have a bigger standard deviation. So let's calculate the correlation to see if this is true or not. Okay, so correlation, again, we do the same thing. We put in the two arrays of numbers. In this case, we get a pretty strong correlation, 0.826909, right? It's pretty close to +1. Okay, not quite +1, but pretty close. How about over here? Correlation, okay, first set of numbers. Oops. Sorry about that. All right, so let me get back here. Let me try that again. So this is the first set, and this is the second set of numbers. much smaller, 0.29811. So you can see that even though this had a much bigger covariance, it really has a much smaller correlation. In fact, let's even try and plot these, see if I can do this correctly here. Okay, so I'm going to plot A and B, and I'm going to try and do a scatter plot. So let's see if we can do this correctly here. So I have this scatter plot right here. Let me see here. Let me see if I can make this a little bit smaller so it fits here a little bit better. And let me just draw in, I don't like the grid line, so let me draw in a trend line here. You can see, seems to be a pretty strong positive relationship. So that's A and B. Let's try C and D. So again, let's try and draw a scattered plot. And again, let me make this a little bit smaller and kind of move this over here. And let's try and, again, fix that, draw in a trend line. You can see this doesn't seem to be as strong a relationship as this graph here, right? And that makes sense. This one has a correlation of 0.29811. This one has a correlation of 0.82609. So even though the covariance was much smaller, the correlation was much, much larger. Again, it's these larger units that cause the covariance to be large. All you can say here is there's a positive relationship, and there appears to be a positive relationship, but it's not nearly as strong a positive relationship as it is for A and B. So I hope that clarifies the difference between covariance and correlation.